everybody. So today we are on page 31, which we are going to talk about how to convert, we done yesterday how to convert polar points and rectangular points into different forms. Well, today we're going to talk about what if I have an equation. How could I rewrite an equation from rectangular to polar so you could plug in polar coordinates to it? Or take a polar coordinate equation and turn it back into a rectangular coordinate equation, which is a little bit tougher. And this is what we're going to do the little Zoom class meeting in this week. So if you come join me on Wednesday from 2 to 3, and I think I said different times in earlier videos, scratch that. 2 to 3. 2 to 3 on Wednesday, we're going to do a little Zoom session, work together on this in place of the alternate assignment. So just be mindful, if you don't come to that Zoom session or you can't come to the Zoom session, that's okay, but there's an alternate assignment you need to complete at the end. And if you come to that Zoom session, then you get credit for that assignment. So make some time for that if you can, 2 to 3 on Wednesday. Okay, so let's jump into this. So talking about converting polar coordinates, and zoom in a little bit so you can see a little bit more clearly. So let me zoom in. So the first part's pretty easy. If you're rewriting rectangular equations into polar equations, it's pretty straightforward. Anywhere you see an x value, you're going to take that x out and replace it with r cosine of theta. Now be mindful of that if you have something like 3x squared, well, when you plug that r cosine in, you've got to plug in 3r cosine of theta squared, which means that squared gets distributed to the r and the cosine, so you end up with 3r squared cosine squared of theta. So just be mindful of that when you plug those things in, that's what it should look like. Take that off real quick. And then anywhere you see a y, you're going to plug in r sine of theta. Those things also probably look familiar because that's what we use when we were talking about solving magnitudes and changing magnitudes into their different forms. So probably looks a little bit familiar. So again, anywhere you see an x, put in r cosine of theta, and anywhere you see a y, put in r sine of theta. And I believe that brings us to our first example already. It does. Don't look at that yet. Don't look yet. Okay. Convert these polar equations. So let's jump over to example 1. Example 1. Boom, zoom, boom, boom. Look at me go. I zoomed in too far. Okay, so I have these two equations that I want to look at. Two equations that I want to talk about converting into their polar equation form. So again, remember the key to this is that you remember your two formulas. And where we see an x, we have to plug in r cosine of theta. And anytime we see a y, we have to plug in r sine of theta. And you can easily remember that. Like, remember that the x value is cosine, right? And the y value is sine on the unit circle. So that kind of helps you remember that x goes with cosine, y goes with sine. And so over here, let's go ahead and try that. Where that x is, I'm going to put parentheses r cosine of theta squared. So the x right here became this r cosine of theta, and then I keep the squared. Plus, parentheses, I've got y plus 3, so I'm going to replace the y with r sine of theta plus 3 squared equals 9. And so now it's a matter of working through that and solving that. So over in this first part, hold on, I lost my pen. There we go. Again, we're going to distribute the squared all the way in, so it becomes r squared cosine squared of theta plus. This one's a little bit tougher right here because you can't just distribute the squared to an addition problem, right? Over here in the cosine, we could distribute the squared because it's a multiplication problem. But when we have a addition problem or subtraction problem inside, we have to think about it as it would be written out completely. R sine of theta plus 3 times r sine of theta plus 3 again equals 9, which ultimately means I'm going to have to distribute this here, and then distribute the 3 here and here. Do our FOIL method. So ultimately I end up with r squared cosine squared of theta plus r sine of theta times r sine of theta is going to give us r squared sine squared of theta. R sine of theta times 3 is going to give me 3r sine of theta, and then 3 times r sine of theta is going to give me another 3r sine of theta. So ultimately I'm going to have plus 6 r sine of theta. And then 3 times 3 is going to give me plus 9 equals 9. From there, it's just a matter of doing some simplifying, right? You can see pretty quickly here, if I subtract 9 from both sides, that 9 is going to cancel, and I'm going to be left with a 0 over here. Looking at some other simplifications that I can do, I also notice that if this and this both have r squareds on it, I could factor an r squared out. So I'd end up with r squared on the outside, so I have cosine squared of theta left here. And if I factor an r squared out of this, I'm left with sine squared of theta. And then I have 6r sine of theta here. So the last real simplification step I can see right there, let me switch to another color again one more time. The last major simplification I see here is sine squared and cosine squared. We know that from our trig chapter, right? Sine squared plus cosine squared is equal to 1. I know you said that out loud because that's an easy one to remember. So I'm going to take that parentheses, cosine squared plus sine squared, and change it to a 1 plus 6r sine of theta equals 0. And that last step then, r squared times 1, well, we know r squared times 1 is just going to give us r squared. So I end up with r squared times, I missed the s, 6, I missed a lot there, hold on, backtrack. 6r sine of theta equals 0. And that would be my polar form of that. It's a little bit long, but it's mostly just algebraic simplifying, right? R squared plus 6r sine of theta equals 0. And that would be your polar form of the first equation. So with that, let's take a look at the second equation. If you need that, make sure you pause. I'm also going to put up the nicer version of it in just a second with my actual notes that is a little bit more clearly written. Go away. Okay, so let's take a look at the other one. X squared plus y squared equals 9. So x squared plus y squared equals 9. So where this x is and where this y is are going to be my two replacements. My x is going to become r cosine of theta squared, and the y value is going to become r sine of theta. So r sine of theta squared equals 9. And so we're going to do a little distributing here, kind of distributing, right? This squared gets applied to the r and the cosine here, so I end up with r squared cosine squared of theta. Over here, this squared gets applied to the r and the sine of theta, so I end up with r squared sine squared of theta equals 9. And just like in that last problem, I can see right here that I could factor out that r squared. So if I factor an r squared out of r squared cosine squared of theta, I'm left with cosine squared of theta. And if I factor an r squared out of an r squared sine squared of theta, I'm left with just a sine squared of theta. So you can see if I were to redistribute this r squared back in, I would go back up to where I originally was. And then this is just like that last problem. Sine squared plus cosine squared, we know that simplifies to 1. So r squared times 1 is just r squared. And ultimately that tells me that r squared, let me come over here, r squared equals 9. And there's one more simplification step there, and that would be square rooting both sides. And we would get that r is equal to 3. Now, I know technically it would be r is equal to plus or minus 3, right? So I could put the minus 3 there, but when we're talking about polar coordinates, like the radius is the radius. I know we could make the radius go to negative, but we're not really going to do that very often. You're just going to leave it as that r equals positive 3. It's a positive radius of 3, which means that we would have a radius of 3 that goes around in a circle, which makes sense, right? X squared plus y squared equals 9 is the equation of a circle. R equals 3 is the equation of a circle in a polar form. So that covers that example. Okay, coming back into our notes then. We have the nice versions of them there if you want to see it written nicely. That's my nice version there. Almost. There we go. There's the nice one. So if you want to pause that so you can write down those nicer ones, please go ahead and do that now. I'm going to go ahead and move on. Okay. So rewriting polar into rectangular is a little bit tougher. You got to use a little bit of critical thinking. You got to be use a little ingenuity to figure that out. And that's literally the directions the book gives. Use ingenuity to figure it out. With that said, we're not going that far into this. We're going to do a couple examples, and if you can figure out those few examples that are pretty consistent every time, you'll be able to figure this out going forward. So just remember these 3 examples, and that'll really help you. And like I said, if you come to that Zoom meeting on Wednesday, it's going to help a little bit in understanding what's going on here, because we're going to work together on it. So I've got 2 examples we're going to look at. Sorry, 3 examples we're going to look at in example 2. Okay, so here's my 3 that I want to look at. in the first one it says r equals 2. Well, if you remember from the last example, you just wrote down an example, part B in example 1. You know what this should come out to. R equals 2 gave us one of the equations we had earlier. We know that r equals 2 would make a graph of a circle with a radius of 2 in the polar coordinate plane. So what that tells me is ultimately this should be a rectangular equation of a circle with a radius of 2, which I know if you don't remember geometry super well, it might be a long time ago that you did this. Here's what we're going to do then. We're going to take this r equals 2. And ultimately what I'm going to do is I'm going to start by squaring both sides. If I take r squared and 2 squared, we end up with r squared equals 4. Well, there's a really important formula that we know. We know that the x squared plus the y squared in the polar coordinate plane equals the hypotenuse squared, which we refer to as the r in the unit circle. If you remember back when we did unit circle, we always called the hypotenuse the radius, the r. So I know that r squared is equal to x squared plus y squared. Again, just to show you this on a graph, if I put this point over here, the x value on the bottom and the y value on the top make up the right triangle, and the radius is this piece here. So x squared plus y squared equals r squared. I know that's a horrible right triangle, but just pretend it's nice. X squared plus y squared equals r squared is a squared plus b squared equals c squared. So I'm going to take that r squared out, and I'm going to plug in x squared plus y squared instead, and I keep my 4. And that would be the rectangular form of a circle with a radius of 2. Coming over to this next one, I'm going to switch the colors so we don't blend them together. Okay, theta is equal to pi over 3. This one's a little bit tougher, but again, there's another formula that's really important to remember. We know that if we take the tangent of theta, we always get the y value over the x value. Again, that comes from this little right triangle setup, right? If I put this over here, sorry, let me try making it look somewhat decent. There we go. There's the right triangle. Again, this is my x value, this is my y value. If this is theta, tangent is equal to the opposite over the adjacent. Since the y is opposite and the x is adjacent, that tells me that the tangent of theta is equal to y over x. So what I can do is I can take the tangent of both sides in this problem. Take the tangent of theta so long as I take the tangent of pi over 3. As long as I do it to both sides, it's totally okay. So tangent of theta, can't do anything with it because I don't know what theta is, but I can take the tangent of pi over 3. Think about your unit circle. Pi over 3 is the 60-degree mark, so if you use the little hand trick, it would be like that. So the 60-degree mark would be putting this finger down. So what it tells me is that the sine value is radical 3 over 2, and the cosine value is 1 over 2. Or the y is 1 over 2, and the x is 3 over 2. So I'm going to have y as, make sure I'm doing that right, tangent is equal to 1 over radical 3. I'm putting down the wrong finger. I'm trying to do it backwards for my camera. I think I said that wrong. The cosine would be radical 3 over 2, and the sine, no. Michael, Mr. Knock. I'm having a moment, I'm sorry. I hope you all got that on your own. That's what I'm trying to articulate to you. The tangent of this would be the sine over the cosine. The sine is radical 3 over 2. The cosine is 1 over 2, so it ultimately ends up being radical 3 over 1. So tangent of theta equals radical 3. Please look at your unit circle if you got confused there. I'm trying to articulate that and look at a backward camera and confuse myself. So ultimately, we know the tangent of theta is radical 3. So I have to say to myself, great. If the tangent of theta is radical 3, then I take the inverse tangent of both sides. Let me make sure I'm writing this. I've totally just confused myself completely. I think I'm doing something wrong. I apologize. I apologize. What am I doing? Help me, guys. Help me. Okay, duh. That's where I'm good. Okay, so here up to here is good. Phew, pause. I was trying to like undo. I'm like, if I took the inverse tangent of both sides, I'm just going back to where I was. Once you get to this step, since we know that tangent of theta is equal to y over x, what I'm going to do is take out the tangent of theta and replace it with y over x. So I end up with y over x equals radical 3. And my last step, multiply this side and this side by x. That cancels, and I get y is equal to the square root of 3. Again, if we think about that graphically, right? Graphically, as a polar coordinate, it says theta is equal to pi over 3. So what we know is that's going to be this that goes this way, but also this line that keeps going this way. It ends up making a linear equation, right? Because this is my 60-degree mark going up this way, but it's also 60 degrees from here. So it makes that linear line. And if you think about this graph, I forgot the x there, sorry. Y equals radical 3x. Well, that's just saying that if I took a linear graph, my y-intercept is 0, and then my slope is radical 3 over 1. So it creates a line that goes that way, exactly the same as the graph above. So they mean the same thing, just one uses a direction and one uses a slope to get you there. All right, this last one. Shimmy that over like that. Change to one last color. Let's go ahead and do red for this. So the last one is the r equals the secant of theta. And I'll rewrite it down here just because it's a little disjointed, but this is part C. So r secant of theta leads me to a little bit of a problem. I don't have a formula, right? Tangent of theta equals y over x, and x squared plus y squared equals r squared are your two universal formulas that you can use. I don't have a theta here, and I don't have an r squared here. I don't have an r squared currently here, right? But we can easily make an r squared. Again, the same thing as the last time is that I square the left-hand side. The difference being, in the first one, we squared both sides because the right side was a number. It was a constant, so if I squared it, it went away. If I square both sides here, I'm going to end up with secant squared, and I don't have anything to do with secant squared. So we're going to do this one a little bit differently. In this problem, instead, what we're going to do, because if I square both sides, like I said, if I square both sides, that secant's going to get confusing. Instead, we're going to try and rewrite this equation first to make it a little bit different. So what I'm going to do is rewrite secant in terms of sines and cosines. So secant would be 1 over cosine of theta. Well, then I can rewrite this equation as times cosine of theta times cosine of theta on both sides. These would cancel out, and I end up with r times the cosine of theta equals 1. Well, what's nice is you know what r cosine of theta is, so that's the conversion we're going to use in this one. We're going to use those conversions that we use for our polar coordinates. R cosine of theta represented the x value, so this is x equals 1. And that's how we do that. Again, this came from the fact that x is equal to r cosine of theta, and y is equal to r sine of theta. So those three things, if you could learn those three examples, you're pretty much set. There are some harder ones. There are definitely some harder ones that could pop up, but we're not going to get really into that. These are the three that you need to be comfortable with. If you see something that has that r is equal to a constant, you square both sides and set up the equation of a circle. If you see that theta is equal to some sort of radian or degree measure, you're going to take the tangent of both sides and use the tangent of theta is equal to y over x. And if you see that the radius is equal to something like secant or cosecant, you're going to go ahead and just multiply both sides by that reciprocal, right? And that should get you going in the right direction. So again, come make sure you check out that breakout Zoom session. I think that will help a lot on these problems. Because you'll be able to ask questions directly, work with me through these. Like I said, it is a lot of ingenuity. It's a lot of you thinking critically about what you can do to rewrite those equations. Kind of like those simplifying the trig expressions, or simplifying the trig problems into simpler trig problems. That was a little bit tough for us in class. So there's my nice version so you can see it a little bit less chaotic, a little bit more organized. Please let me know if you have any questions. As always, I'll talk to y'all later. Bye.